In this lesson, we'll discuss the effect of acceleration on tension of a cord. With that being said, the first of two questions reads, a 12 kilogram flower pot is hanging by a cord from the roof of an elevator. What is the tension in the cord when the elevator is stationary and when it's accelerating upwards 3.0 meters per second squared? Okay, let's begin with an illustration. So this rectangle represents the elevator, and hanging from the middle is a flower pot. Newton's second law says that if we take the mass and multiply it by the acceleration, we get the total force. What are the forces acting on this flower pot? There is the force due to gravity, which can be represented again using F is equal to m times a, where a is the acceleration due to gravity, so I'll just replace it with a g. And there's also the force of this tension, which is going upwards. We need to take the difference of the magnitude of these two vectors. So if I call this vector t, I need to subtract that from the magnitude of this vector, which is mg. So I'll replace this f with t minus mg, and that is equal to the mass times acceleration for the total system. When something is stationary, the acceleration is equal to 0. So if we replace this 0 in for a, we get t minus mg is equal to 0. And rearranging this formula by bringing that over, I have tension is equal to mg. And that makes sense because if something is stationary, it's at equilibrium, so the forces are all balanced out, the upwards and downwards force in this case. Therefore, to find tension when things are stationary, we take the mass of the object, being 12, and multiply it by 9.8 meters per second squared. Multiplying these numbers out, you should end up with 118 newtons. Then you can verify that on your calculator, shown here. Of course, I've rounded it up. Now let's try to find the tension when the elevator is accelerating upwards at 3.0 meters per second squared. We'll use this relationship again. Remember, t is what we're looking for. So t minus 12 times 9.8 is equal to a mass of 12, and the acceleration is 3.0. Rearranging, we have t is equal to 12 times 3.0 plus 12 times 9.8. Let's use our calculator. So we'll add 36 to that because 12 times 3 is 36. And we get around 154 newtons. 154 newtons. So that's one way to approach this problem. Let's move on to question number 2. A rope fastened at the top is hanging over a cliff. What is the tension in the rope with 70 kilogram mountain climber sliding down the rope at a constant acceleration of 6.0 meters per second? So to do an illustration, we have a cliff that looks like this, and there is a rope that is hanging down like that, and there is a person climbing that rope, and specifically in part A, they're sliding down. To solve this problem, let's recall a formula that we used earlier, which was this part, where we had t minus mg is equal to ma. T is what we're looking for, so if I bring that over, I have t is equal to ma plus mass times gravity. The mass is 70 for the climber, and the acceleration is downwards, right? They're sliding down, so we represent that with negative 6.0 plus the mass of the climber times 9.8, the acceleration due to gravity. So using our calculator, we have 70 bracket negative 6.0 plus 70 bracket 9.8, and that gives us 266 newtons. Now notice something interesting about this answer. If the person was hanging on this rope and not moving, being stationary, the tension on the rope would be 686 newtons. Now notice that by accelerating downwards at that particular acceleration, the tension on this cord is only 666 newtons. So accelerating towards gravity, reduces the tension of that cord. Just keep that in mind. For question B, what is the tension in the rope if the climber is accelerating, climbing up the rope at a constant acceleration of 6.0? So in this case, you would add them together, 686 with 266. 686 plus 266 gives us 952. 952 newtons would be the tension exerted on this cord. And so there you have it. That is how to find the tension when accelerating up or down.